what we're going to talk about is the McWest Metabunk calculator. Okay, everybody's familiar with it. I see people going through all kinds of heartbreak over it and nonsense, and I don't know exactly what to think about it, but I did some thinking about it this week, and ironically, the thinking started out with trying to come up with a rebuttal for a Wolfie 6020 video, which I did, but in the meantime, I woke up at, get this, 4:20 in the morning with this revelation about McWest's curvature calculation. And so that was pretty funny. And I kind of laughed about it and woke Cammie up, and she's like, "What are you laughing about?" And I told her, but anyway, it was pretty funny. And so there's a few things I want to say about this. And of course, many of you know that I have stated many times that this idea of standard atmospheric refraction is nonsense. The reason that I say it's nonsense is because there are way too many variables to call anything standard. I know how the weather is in Colorado, and certainly I'm sure this is true for just about any place in the world. At any part of the day or night, refraction can change dramatically because of temperature coefficients, because of barometric pressure, because of humidity. To call anything a standard refraction is absolutely the height of folly, in my opinion. And I think I can back that up with pretty good evidence, because we know that the atmospheric conditions change virtually at every moment during the day. So the idea of the standard atmospheric refraction is just silly. Okay, so basically what I want to say about this is that what McWest does in his calculator, okay, is they make an assumption, and that is that as you are looking through the atmosphere of the Earth, obviously it becomes thicker and thicker and thicker the further out that you look, or the further out that you're observing. The result of this, of course, will cause the horizon to drop, right? Well, okay, I think we can all agree with that. And I'm actually going to kind of show a part of Jaren's video, one of his recent videos, to kind of illustrate that point. But so Mick has taken this idea and he has kind of borrowed it from this International Standard Atmosphere calculation, and they show, they explain their thinking, and for the most part, I agree with it as far as, their variables that they're using. However, to call it, standard, once again, I don't agree with that, but I do agree with the variables that they're putting into this formula, and they're kind of taking an average, I guess. But that average is far too wild to really apply to anything and call it gospel. All right. But what I'm going to show you can be taken as gospel, and I'll get to that in a minute. So anyway, McWest also has a empirical evidence and derivation, and he explains how it all works. And basically what he says is that it's calculated, it comes down to a calculation of 7.6 times r, which is the radius of the Earth, which gives you basically a bigger Earth to work with, right? Not literally, but figuratively. And, because he's saying that because of the atmospheric characteristics, this is actually what it kind of equates to, is if you increase the Earth by another 1/6 of its radius, then you will have basically the standard refraction that he is claiming. Well, that's all fine and dandy, but so let's look at a few things, and I want to go ahead and play Jaren's video on this, and I want you guys to pay close attention to what Jaren shows here in this glass refraction experiment. And indeed, what Jaren is going to demonstrate very clearly is that when you look through a medium, and in this case it's water, and I have to remind everyone that our atmosphere is actually technically considered a liquid, so it is not outlandish to use this as an example. But basically, if you are looking through a glass of water, you can come up with a simulation of what it would be like to actually increase the density of the atmosphere. So let's watch this for a second, and then we'll continue on.
What's going on, everyone? Jaren from Jarenism here, and we've all seen the arrow behind the water trick before, right? Well, let's pick it apart a little. Watch the arrow closely and tell me, does it drop or rise? Clearly, the arrow drops. Here I'm going to lay an overlay over to show that the image does definitely appear lower. Why? Well, because we're looking into a more dense medium. Let's place a horizon line behind the glass. Since our air can be seen as a liquid, and when we look off into the distance, could this be the cause that the horizon lowers? Does this curved horizon match our reality? Close, but we have a problem. You see, the arrow and the horizon are flipped. The water flips the image, and that doesn't happen in reality. Well, or does it? Let's switch glasses here to a square glass. Aha, there we go. Now we see a dropped horizon in the distance, and we see a non-flipped image. In fact, we're starting to see some Fata Morgana effects as well. So exactly how does this compare to reality? Well, when we're on a beach looking at the horizon, we are looking through a large slab or a box of air with increasing density, which means where you stand is the least heavy density. As you look out and across the water, the density increases as we have seen. Images will drop down. And if you really want something interesting, here's some food for thought. When you're at the beach looking out or across the water, you're in the lowest amount of atmosphere, trying to see something that is through the heaviest amount of atmosphere, and things will appear to lower. Now, when you are looking straight up from where you are, you're actually in the heaviest or densest part of the atmosphere, looking into the least dense part of the atmosphere straight above your head. So when you understand both those predicaments and that they coexist, then you'll understand that you really kind of do exist in your own personal atmospheric dome. Now, we have seen that viewing objects through a square glass results in that object being seen lower and that the object will not be flipped. But we also know that the curved glass that causes images to be seen lower as well also shows those images as reversed. Anyone have anywhere where they've seen things flipped in our reality? Yes, I'm talking about the counter-rotation of the stars, but there is so much more that this could help us uncover. Now, you could simply call it crazy because it goes against your deeply held religious beliefs, and so you may choose the mainstream explanation instead. Then you'll be told that light must be a wave and a particle, because that makes sense. They'll tell you that light is always traveling at the imaginary speed of light, but it slows down? How does it exit at the speed of light if it slowed down? Well, it didn't slow down. See, it became a particle, and then, still tracking at the speed of light, it decided to dance with other particles before exiting again as a wave at the speed of light, breaking the second law of thermodynamics, but who's counting, right? Say we have a box and we add water. Then we shoot a light beam, and it slows down when it hits the water, but then exits at the speed of light again? Well, you can believe that if you want. I find it to be madness. Typical ad hoc nonsense, theories pushed as fact. And we need to now think, is it possible that we are seeing things flipped in our personal atmospheric ordered domes? Well, just another question that needs testing. But what's clear? Well, clearly all things in the distance drop off because the atmosphere that we view through is increasing in density. So geodetic surveyors, they definitely take this drop into account, right? They take it into account, right? Oh boy. Nope, actually, they don't. Even though we just proved it, they simply ignore it. Wouldn't want a little truth mucking up your 400-year-old deception now, would you?
And there you have it. No, you wouldn't want any truth mucking up your deception, but it gets worse, ladies and gentlemen, much worse. And we're going to demonstrate that very quickly. So, Jaron, go ahead and I'm going to kick it over and you can share your screen. And I'm going to explain why Mick West's calculator is not only wrong, but it's backwards. Okay? All right, guys. So what I want to do is I want to go through a little mental exercise with you guys. Right? Now, obviously, when we look out into the atmosphere and we see things drop on the horizon, that is absolutely as a result of refraction. However, what would you guys say if I told you that that refraction would only work on a flat Earth model? Oh my God, Bob must be crazy. What did he smoke this morning, right? Well, it's not that way, okay? So here's what's going on. And this is the thing that I found absolutely amazing when looking through the way that Mick West derived his atmospheric refraction, his standard, and all this. It turns out that it is based on a flat Earth model. How do I know that? It's simple. Okay, here we go. So what you need to do is picture this in your mind. Let's say I have a laser, right? And I'm standing on a ball Earth. Now, mind you guys, on a ball Earth, this is a heliocentric model. We are on a ball Earth for this example. I take that laser, it is perfectly level, and I fire it off into the distance, okay? Now, according to the ball Earth heliocentric model, as that laser beam goes out, then what's happening? The Earth is actually dropping out from underneath it. So what's happening is that the distance between the laser beam and the Earth is increasing, right? So when you go out 10 miles, you basically got a 66-foot difference between the laser beam and the surface of the Earth. If you extend that beam out to 100 miles, then you have got nearly 7,000 feet of distance between that laser beam and the Earth. Okay, are we on the same page so far? All right. Now, what happens when you go up in elevation, guys? The atmosphere becomes thinner, doesn't it? It becomes less dense. And what happens when you fire a light into an atmosphere that increasingly becomes less dense? Well, exactly the opposite of what happens when you fire a light into an atmosphere that becomes more dense. Instead of refracting down, it will refract up. Okay? So, do we have that in our heads? Okay, great. Now, let's take it back and let's apply this little mental exercise to Mick West's curvature calculator. Okay? The problem is again, like I said, it is not taking, in their own model, it's not taking the curvature of the Earth into consideration, which of course should take it from 7/6 radius to 6/7 radius, which would actually make things worse for them, right? So this is, you know, when I realize this, it's like, oh my God, how is it that nobody has ever really caught on to this, right? It's as simple as you can get. So if we look at Jaren's diagram here, on the right, what we're seeing is we're seeing the laser beam that's right here, okay, and he's taking it out, and the gradients of blue are basically different gradients of atmosphere as you climb above the Earth, right? So it's rising and rising and rising, and what's happened, as Jaren is showing here, is because the atmosphere is becoming less dense in each gradient, or, you know, maybe perfectly linear, that beam is going to refract upwards, not downwards. Holy smokes. Well, that throws a big wrench in Mick West's curvature calculator, doesn't it, guys? In fact, it makes it complete BS. Because, once again, there is nowhere that they take this Earth curvature into their formula for this differing gradient as you are looking further and further into the horizon. Now, I will say that over short distances, it won't make a whole lot of difference. However, when you start getting into the idea of very long distances and very long observations, then this becomes a very, very critical factor. And this is undeniable, guys. I mean, this is absolutely undeniable. And as I can see some clowns in the chat telling me I don't understand how light refraction works, I'd like to see you explain how it does work, because this is how everybody understands it. In fact, this is how Mick West is portraying it to work. So I don't think I'm wrong on this, guys. And if I am, I'm open to that, but I don't think so. John and Jaren, what do you think about this idea?
Well, I think, you know, when you're looking at any kind of diagram that they're showing us of what's happening during refraction, they completely give up the idea, and this is what we see them do all the time. They give up the idea of parallel rays. You know, it's always as if they've been taught, and this is the whole point of school, is you're taught a certain way to handle each individual problem, and they want you to answer it in a certain way. And so you learn to understand how refraction works when you're talking about the sun being higher than, or seeing the sun higher than it actually is. But everything that they do, it completely abandons everything else that they've taught you. Like, for instance, the rays all hitting us parallel, because then they show pictures like this where it simply doesn't make sense. They're talking about here, you know, we're saying here we shoot this laser, right? You shot this level laser out, and we said it would refract up. But they're showing here that the light goes down. And why are they showing that? Because they're saying we see the sun higher than it actually is. So, I mean, to me, it's such a disaster that they've completely destroyed any idea of what would happen. Because, again, if the light is coming from the sun and then it's hitting a heavier medium, then yes, it would bend down, and then it would bend down, and then it would bend down. But again, if you're shooting a laser in this direction, would it also hit a lighter part of the atmosphere and bend down? Down, down? No, it would bend the opposite way. You're shooting it from a heavier to a lighter, it should refract up. And that's basically what you're saying, right?
So that is exactly what I'm saying. And again, like I said, when you look at the Metabunk calculations and the way that it is derived, they basically derive it from a refraction standard that comes in from the lights above, directly above us. And of course, that is probably where the least amount of refraction comes, especially when something is directly above you. Theoretically, like when the sun is directly above you, it would have by far the least amount of refraction because it's coming straight down, and it wouldn't necessarily be going through any changing density gradient except on a vertical axis. So, yeah, I mean, I don't know what else to say about that. It is about as straightforward as you can get, and it completely refutes the idea of the 7.6 times R formula that Mick West has got going on, So, I mean, guys, just throw that in the trash. You're better off with just a standard refraction calculator.
And I'll show people why they have to do this, why they have to say that we see the sun, this is its true position, and we perceive it to be here. And the reason why is because when you watch a sunset, we see this. And here's a picture of it. So when we see a sunset, we should be seeing the yellow sun setting in a time period commensurate with it, remaining equal and going down at a step rate. But what we actually see is this bright orange sun. We see the sun kind of get squished because it's going away from us. And they have to be able to explain that. They can't just say, oh, well, the Earth's flat and the sun is actually moving away from you, not setting as we've told you. So they had to come up with a reason. And this is their reason. They're saying when the sun is here, it's actually really where the yellow sun is. And when we see it here, it's really where this sun is. So when we see the sun setting like this at its last moment before sunset, they're actually saying the sun is well below the ground because it needs to move at that speed. It needs to keep up with it. And it doesn't. And the reason for that is because the sun is not setting below the horizon. The sun is going off into the horizon. So, I mean, that basically is why they talk about this whole idea of refraction in the way that they do. Now, Mick West and using it as a standard refraction. I mean, there's no standard refraction. He's using it to lift things up over the so-called curve, which, again, is just impossible. Nothing's being lifted up over any curves. I mean, that's what they're basically saying is that you would have, if I go back to this image here, let me get that one. So we go back to this image here and imagine that, okay, so what they're saying is that, and let's just give them what they have here as being true. They say because the sun is in its true position here and it's being bent to the observer and we're observing it here. So they're saying the same thing happens with a mountain. Okay, so they're saying if you have a mountain, let me get a color here, maybe brown. All right, so they're saying if we have a mountain set here, say Canigao is here, and they're saying that it's being displayed up here. Okay, but the problem with that is the mountain is not going through a change from the least amount of atmosphere to the most amount of atmosphere. It's remaining in the same medium. So how is it that we're going to call what's going on here, which is true? Okay, I'll give you that. The sun is in the least amount of atmospheric distortion, and as it enters into more and more and more and more, that it's going to affect the speed of that light or, the way you view that optics, however you want to describe that. But it doesn't happen here because clearly this is the same area of the atmosphere. This is the same density layer, and so the mountain is not going to all of a sudden be up higher than the horizon. And again, whenever we see that happen, we see the mountain where? The mountain displays right on the horizon. Where do we see the buildings in Chicago? Across from Lake Michigan, we see the buildings appearing right at the horizon. This is where we see these buildings. So would it be that you would see buildings here and somehow because of light doing refraction, that it's going to lift this item up and place it exactly at your horizon? No, there's no way. Clearly, they're just using different, I mean, to say that this is why we see things further than we should is ridiculous. It has nothing to do with this idea of refraction. It's just you're seeing items that are actually there, and it's different than, there's more clear atmosphere that's causing you to see that. Or possibly in the case of Kanagawa, you're only seeing it because the sun is setting behind it, which is kind of creating a silhouette of that mountaintop. So, I mean, really, when you get into like Kanagawa and those kind of places, I mean, I got kicked out of Metabunk 3 or 4 times. I keep trying to go back with a different username, but they find out it's me somehow. But when I try and go back there, and argue with them, it's always about, Kanagawa and these places that are supposed to be 3,000 or 4,000 feet below the line, and then they'll just say, oh, well, with the standard refraction, it's only supposed to be 1,000 feet below, and okay, it's an extreme case, so it's good, but it's like, no, you're seeing almost the entire mountain. And then they'll always say, well, how come you don't see, how come water is covering these buildings? How come we see some water, why don't we see the shore? And really, if you get into that whole idea, and I'm doing a video on that coming up, because that has to do with the same thing. It is looking through the medium, and when you're looking through, if this man is looking through, I'd have to draw a flat earth. Let me do that, actually, just show you that since I brought it up. Okay, so if we get this view here, and we're looking through a flat earth, there we go. All right. And if you're talking about this person here and he's looking and seeing water in the distance, well, because things that are lower than your eye, and if you're talking about light traveling, that light coming to you, the way it would refract is up. Something, it's refracting up as it's getting from a heavier to a lighter density, and therefore the water is actually higher in our eyes because we're actually observing a 2D picture plane. You have to kind of picture everything that we see has to display itself in our, I guess you want to call it our picture of the earth, our picture of reality. And that's why when you look further in the distance and we see more and more things, they have to be scrunched into lesser and lesser area. But as far as looking across the ocean, you're looking at a huge body of water, and that actually lifts up. And it'll be better in the video for me to describe it. I have to show it. This is not the right graphic. This graphic here is just showing where we see the sunset. I'll have to show you this. This is kind of not ready yet.
To add to that, also, guys, when you're looking across bodies of water, as Rob Skiba demonstrated so very well with his looking across at the Chicago skyline, right? There is a distinct atmospheric lensing effect that actually magnifies things off into the distance, right? This is something that is absolutely true, and even I loved it, especially when he had the weatherman that said, "What you're seeing here is a mirage." Actually, talking to the expert, the atmospheric expert, and he's saying, "Oh yeah, you can definitely get these atmospheric lensing effects that will magnify things." And I think Rob Skiba demonstrated that absolutely in spades. So, there's been a lot of criticism for people, saying that, "Oh well, you can't demonstrate the atmosphere like that," and it's like, why not? It's a perfectly valid demonstration, and it matches precisely what we do see in the real world. So, I just don't even understand that objection. But then again, that's what people do. That's what a lot of the ballers are paid for, honestly, to do that. Or their cognitive dissonance simply does not allow them to see the extreme logic that's right in front of their face, as well as this straight up demonstration.
Yeah, this picture is kind of the one I was getting at. When you're looking across at, say, this lighthouse here, that the atmosphere is the most heavy right above this water. This is the most distorted, right? The whole way through here is where you're going to have the biggest change. And so you kind of get that convoluted, but it's also acting as a lens. And so you're going to actually see this water magnified and appear higher than it really is. And then if you want to see why we see more when we go higher, is because as you get up here, now let's say that you get up on a cliff and you're looking down at this lighthouse. Well, now you're able to look over or across, and you're not getting this heavy distortion here. And that's why, when Wolfie is at beach level and he's 3 feet or 3 meters above sea level, and he's showing that this lighthouse is blocked by the water, and then he gets up at 100 feet and shows that it no longer is. Well, this is all that's happening, is when you're at the beach, you're looking through that lensing and that distortion, which causes the water to appear to do this. And when you get up above that, then you are seeing above that distortion, and you're actually seeing the whole lighthouse. So that's what's going on with the water.
Yeah, I think this brings up an important point that you've got two different operations of refraction going on in terms of one operation of refraction for heavenly luminaries and then a whole separate operation of refraction for objects that are near the ground. And so if you assume a flat Earth, this all makes perfect sense in both cases. So whether it's sunrise and sunset or star rise and star set, or even the counter rotation possibly of the southern stars, that makes a lot of sense when you factor in refraction on a flat Earth. And at the same time, so too makes a lot of sense the observations of ships or cityscapes distant along, a water horizon appearing to drop lower and lower down along a curve. So it's not actually the Earth that's curving; it's the light that's curving down. Refracting down, not traveling in perfectly parallel straight lines and giving that illusion of a curve. So this all makes really perfect sense on a flat Earth with refraction in both cases. On the other hand, if you assume a spherical Earth and try to finagle these operations of refraction to work in your model, it frankly doesn't. You have to completely disassociate yourself from what the actual operations of refraction are in order to make this work for a globe. And frankly, that's just ridiculous. But yeah, good points.
Yep. All right. So what we're showing now is basically, I just went through the internet, and these are very easy to find. Little examples of how a changing gradient of medium will cause light to bend. This is no big deal. And what's happened here is this guy has poured sugar in this tank, and as it gets down to the bottom where the more viscous water-sugar mixture is, it is bending that light down. And of course, as he brings it up into the normal water, it bends it right back up, or it returns back to normal. Now, if you were able to go above that, even more, there would be a slight raising of the beam as well. So, in other words,
so Bob, go back to that video again, because I have a question there. Then, so
right.
Why is it then when they show the sun that they're showing the sun and it's refracting to the viewer, the diagram I was just showing, when this is the complete opposite? This is showing that if the sun was where this laser light is, then we would be on the ground, so we would see it. I don't understand where they say we see it lower than it. I'm sorry, where we see it higher than it actually is. If the light is bending that way, isn't this set up the way the atmosphere would be set up?
Yeah,
but they say that because they have to say that, because that's what we observe. So they have to say that that's what you would see. But you're right. I mean, that's as far as I can tell, that's the opposite of what we would see.
It's the opposite. Yeah, that's what I'm trying to get at.
Okay, so what about if you turn it around and remember the sun is the laser point, and then our perspective, from down on the ground would be looking up, essentially towards that bent beam of light, right? Or am I seeing this incorrectly? I mean,
no, you're seeing it right.
Okay, so you're just basically turning it around, and you're looking at it from the sun's point of view, bending down. But if you're on the other side of it, it would bend up, right? Is that what you're trying to say? Maybe I'm misunderstanding you.
No, I guess what I'm trying to say is when they show the sun being that diagram that I had up where they had the sun in its real position, and then they say we're observing it higher than it actually is, right? That's why we see a sunset, and they say you're seeing the sun, and the sun is it's already set, but you're still seeing it. So I'm trying to say, why doesn't that show, or I'm trying to point out, it doesn't show that in that example we just saw.
Well,
so you're saying if they move the pen down all the way, I'm sorry, not the pen, the laser light. If they move the laser light all the way down below the fish tank, that you would then shoot that light up and it would curve to the observer. Is that what we're saying would happen?
No.
Okay.
No. That's not what I'm saying at all.
No, I'm saying, is that what they're saying? Not what you're saying.
Well,
I get what you're saying.
Okay, but this is going to turn into a comedy here because
this is what's funny is that we're trying to deal with this heliocentric model that isn't true. It's impossible to just try and grasp the idea of the ball, and then you're trying to have these layers of atmosphere that are all curved, and the entire thing makes no sense. That's why they show usually their diagrams are such that you have to put the flat horizon, and you have to, because that's reality. It doesn't make any sense on a ball to say that you're looking at things behind the curve of the ball and that they're bending up over it. That's what I'm trying to point out, is that they're not showing it in this example. So I'm confused as to why all of the physics and ray optics are designed in a way that is the opposite of what we see in real world examples.
Right. Well, and there's one other thing that is anomalous about this, and that is the whole idea of how light propagates in the first place. And we sort of touched on this a couple weeks ago, but remember how you were talking about when you shine the light through the tank, and since it goes into the denser medium, it refracts down a little bit. And then, ironically, when it comes back out of the tank, it comes back up. And the mainstream description of this, and this is crazy, is that the light beam is physically slowed down while it's in the water, right? And then as soon as it exits the water, it returns to the normal speed of light. This to me is a non sequitur. That doesn't make any sense. What is it exactly that is speeding it back up to the speed of light after it's been slowed down going through that medium? Right?
Yeah, and I looked it up, and the way they describe it is they say that it's coming through, it hits the water, and then it begins to dance with other particles in the water. It's still moving at the speed of light, but it's dancing with a lot of molecules, and then when it gets released from the water, then it no longer is dancing, and so it goes at the speed of light again. That's the way they describe it.
Oh, okay.
Yeah, that's how I look at it. Like, what do you mean?
I'm going to have to think about that one for a while.
I wonder if they're doing like a conga or more like a chimichanga.
Nope. Salsa.
Yeah, there you go.
Well, obviously, that's when you have to start looking at Walter Russell's model of light propagation, right? Where it's completely different. And honestly, I would like to do a whole nother show on that, to talk about that, because, that explanation, it seems to make a lot more sense. But honestly, I don't feel really qualified to talk on that yet, so I need to do a little more research on it. But there are obviously different models of light propagation as well. And I think, like many things, the one that they feed us, it seems reasonable on the surface level, just like Mick West's standard refraction calculator. But when you really start scrutinizing it, it doesn't add up. It doesn't make any sense at all. And that is so true with so many of the things that we encounter. And that's why so many flat earthers get caught up in these arguments and debates with ball earthers, because we're always, since we've been indoctrinated with the ball model and the ball model physics, it's hard to not defer to them, right? And it's very easy, even when you're the hardcorest of hardcore flat earthers, you still have that brainwashing, essentially, that indoctrination that makes your mind want to go back and reference the mainstream physics model that we've all been taught. And I think that a lot of it needs to be reevaluated. So
yeah, I think people need to rethink light a lot, because when you really start to break it down and think about it, and they describe all of light as traveling, these rays of light are traveling and they're hitting different atmospheric layers. That's fine and dandy. But I mean, really, when you think about looking at a mountain across a body of water, is the light from the mountain traveling to your eye? That's something that, I don't think is true anymore. I think that the mountain is being illuminated by a source light, the sun or the moon, if it's nighttime. But those things are being illuminated by light, and the light is not necessarily traveling to you. Just like, I was talking to Bob the other day and just mentioning they talk about light traveling at the speed of light. Well, if you go in your bedroom and you shut the door and you turn on the light in the room, is the light traveling in the room at the speed of light just constantly in circles? Is it going back and forth and bouncing off the walls at the speed of light? These are just questions I think people need to ask, because I don't think it's as simple as just rays of light.
Yeah, and I did a video pretty recently on the speed of light, because I'm sort of in agreement with you, Jaron, that when you look at the early estimates of what the speed of light is, it was based on, people got the idea because of the moons of Jupiter apparently transiting Jupiter either 16 minutes later or before they technically should have. And so without knowing the distance to Jupiter, even if they thought they did, it would have been wrong. They got this estimate of the speed of light, which was, something like 200,000 kilometers a second or something like that. And then later on, others, a guy named, I want to say Foucault, and then, of course, Leon Foucault, sort of honed that down, doing some really sort of like archaic experiments using rotating mirrors, or using mirrors with a rotating sort of wheel with slits in it, and then measuring like the different angles. And the whole thing is very convoluted, but you know, I heavily disagree with the notion of light being little microscopic subatomic particles, you know, protons traveling at super high velocities and then hitting your eye. You know, I think that that is probably not the case. And I agree. I don't think that the light necessarily has to travel at all. I don't see it as a physical waveform or a physical wave that's traveling through medium at all anymore. But, you know, that's what we're up against, is this dogma of scientism that says, yeah, we know that photons or light is photons traveling in waves through medium, and we can even measure the speed of it. But frankly, I don't think they can. I think that, you know, if light was traveling as fast as they say, they wouldn't be able to measure it using especially the very ancient sort of rotating mirror setups that they did. But yeah, I agree. I think that it's a bunch of pseudoscience in terms of the speed of light and the idea that light is physical objects traveling in waveforms.
Yeah, absolutely true. And also the fact that, you know, it seems like they have taken the speed of light several times over the centuries, and have come up with dramatically different speeds. And now, of course, physicists, for example, in the Sapphire project, are able to slow the speed of light down. And actually, I've read reports on Phys.org that they've actually been able to stop it. Now, I don't know how they did that or exactly how that takes place, but that kind of eliminates the idea of the standard understanding of how light propagates. So, and I'm not claiming that I do know exactly what the mystery is behind that. I do think that other researchers and other visionaries like Walter Russell probably had more of a clue on that than I do. But it's like anything else. I think we're taught the models that will most easily, you know, they seem to make sense, but they really fall down under deep scrutiny. But because of the fact they're embedded into our brains, you know, we tend to want to refer back to them.
The subject of the atmospheric refraction is, you know, is more, I think is the Globers need more the refraction atmospheric as they pretend than the gravity, because there is something that in my channel, I ask for anyone to send me a real example of objects in different altitude, occluding by some artificial horizon, lifting up by standard refraction. Because there is none any experiment that show that, or at least I never seen some real experiment that two objects, you know, in different altitudes, occlude by the horizon, someone lift up in the air. I never saw. I don't know if you have some kind of example of that.
No, it doesn't happen, Irwin. And I have a video I'm working on right now where I'm showing that even by just moving my camera in every different direction I can, when looking through an atmosphere like water, you cannot get an item to rise. That item is going to be lower at all times because it's being retarded. I mean, I don't mind using that word when I'm actually using the right word there. But the light is, you know, the light, or you can say the optics or the observation, all of that is being seen through a medium that is causing it to lower. You can't get it to rise. It doesn't work that way.
My last video is the video that I work in now is based on atmospheric refraction, and I find some, you know, interesting things. Maybe we can share with the people in the chat.
By the way, just so you guys know, this video that I just played just came out this morning by Taboo Conspiracy. Pretty awesome. The guys have a mirror on the ground, and they're spotting it literally on the ground at the shore of a lake, and they're spotting it from 6.5 miles away on the other side of the lake. Love stuff like that. Anyway, okay, Ira, we are now presenting you, so go ahead, sir.
Okay, because one of the principal sites that, and you know, every flat earther or glober enter to calculate the curvature of the Earth is the Metabunk calculator, and this is for me. First of all, I don't understand why in this setup they don't put a field to change the atmospheric refraction, because it's nothing, you know, there is nothing too complicated. If you have made all this situation, all this setup, putting a field to change the atmospheric refraction to make another kind of calculations, that will be awesome. I don't know why they just stick to the standard 0.16 coefficient of standard refraction.
Well, I think I have an answer for that, Iru. I think the reason, first of all, is because Mick West is being deceptive, first of all, and he wants everybody to think that that's going to be the way that it is. And second of all, in order to be able to change that quote-unquote standard refraction, you would have to have pretty much real-time data on the image that you are looking at, right? So it'd be pretty hard to actually come up with a figure to figure into that, right?
Yeah, but I just, you know, I have a calculator from, for example, from Italy, some guys from Italy that they made just the adjustable coefficient of refraction based not on real time, of course, based on some observations of particular day that you know the temperature, the pressure, and you can change this coefficient. But here is not, and I believe this is one of the most calculator used by Glovers and flat earther. And
I don't think it will be after today, man.
Okay, no, but it's sad because when you enter, for example, to the guys from Italy, and also is a Glober, you can have here like a simulation of the atmospheric refraction, but the design is too, you know, it's very bad design. So you must be put here, and you can activate the refraction and put the temperature, the pressure, and the gradient. But it's not more. It's not a nice design. It's not you know, really good precision method to illustrate what you see. And you have here, for example, if you activate the refraction, you can change the temperature of the gradient, and here start to change just this little line there. So it's not very fancy calculator, but at least someone take the time to put that. So that is why I don't understand why these guys, who supposedly are, you know, the Mr. DEBUNK, he didn't. But
that's actually okay. Really good. That's actually really good. So you take the known variables, and it does the calculations for you and adjusts the refraction accordingly, right?
Yes, supposedly yes. I tested with a few things, and you know, match pretty well. But what I'm trying to say is the following: because when you enter here to the atmospheric forum discussion, the last enter in this atmospheric discussion is this video that I showed a few times ago. But even Mike West agreed with this, because this is supposedly is, for me at least, the only video that trying to show an object lift up by refraction. And nobody put any comment on this. Nobody say, okay, that is the example that I trying to find, excellent. But a lot of people enter to this kind of situations, see this video, and believe that the refractions make that, you know, lift up object behind hidden horizon. And this is a deceived video, because the setup for this is completely, you know, there is no a real situation for that. So first of all, that example, for me at least, is completely wrong, because the object is not hid by any horizon. In fact, the sticks are on top of the horizon. When you see this video, for example, you can see, first of all, the surface where the objects are land are flat. It's like, I don't know which is the name of this, like this kind of chair, but it's a flat surface. There is not bent surface, there is no curved surface, nothing like that.
It's like a bench.
A bench, exactly. And then when you see the altitude of the object, you have here the tank of butane, and then you have this box, and the object that supposedly is going to be rise up is on top of those. I mean, it's like this. You have this situation, and the only simulation to trying to say, okay, this is it, what it happened, is the camera orientation, but the objects are not hiding. So when you see this situation where the guys drop the butane gas, which is not an atmosphere gas. In fact, the butane has a value of 1.33 in the index of refraction, so it's very high. It's like put in a glass.
Yeah, very severe refraction. Yes.
Exactly. And it shows like this tiny part of the red stick show is not rising up, is show in the image. That is because, of course, if you have the orientation of this camera, you drop that gas, which is really thick gas. The object is, the light of the object is projected in straight line. So there is the real experiment with this example here.
So it kind of is creating an artificial Fata Morgana above it, right?
Exactly, but not just an artificial Fata Morgana only. The trick is they use the Fresnel refraction, which is something anybody knows in computer physics. It's based on the angle, but I mean, when you see, I created in computer a few months ago because somebody sent me this and say, this is the proof to the object can lift up in the atmosphere. But what they do, let me just go ahead. This is the index of refraction of the butane gas at regular temperature. And when they drop this, yeah.
And I was going to say the other thing is that they don't have any, there's no water, let's say, if we're talking about ocean, in between that butane tank and the thing that's stacked up. So it's the same thing that happened in the Rob Skiba video, where the physicist or whoever that guy is that's talking about the water acting as a lens, and he shows the guy through a magnifying glass the building off in the distance on a wall and says, what do you see? He says, oh, I see the building. It was lifted up. Well, yeah, because there's no water between the magnifying glass and the buildings. If there was, then you're talking about all that having to be magnified. You wouldn't see things lift up over the curvature just like this. Even if we're seeing something, where's the water in between this tank and that thing? Because then you would see more water.
Exactly. But when I recreate this in computer, and I make the same effects based on index of refraction, what you can see it's based on the angle of the camera. If the camera was in front, this never gonna happen, because this is not the object lift. It's creating like a liquid mirror. It's like the gas with this high index of refraction is creating like it was a liquid, glass. So it's just that is why it's distorted. So some of the buildings or the mountain of the city that supposedly lift up in the horizon, they never distorted, are perfectly clear images, which is something that never happened with the index of refraction. For having perfect image without any kind of deformation, it's not based on the change, interchangeable index of refraction like the Fata Morgana produce, or the changes in the temperature produce. When we see the skyline of Chicago, you can clearly see the buildings without any distortion. So I want to address this topic very quickly because we as our flat earthers, we still are waiting for that control experiment to show these supposedly standard refraction lift up objects. And when you start to go a little deeper in this topic, at least what I found was there is a when of course, all coming from the Metabunk calculator, there is this PDF. In this document, which is understanding the astronomical refraction, you're going to have all these situations based on this kind of coefficients. But of course, it's produced by NASA. And this is an old document, 2006. And if you go back in time, there is like the same document, recycle, changing a few things, and you always gonna see the same kind of topic. And even here in Argentina, for example, this is in Spanish, but the first part is in English. This is from the academic institution of one of the province states here in Argentina called Tucumán. And this is something that for me is very, suspicious, because all the time they're going to try to explain the atmospheric refraction. It's assumed to be in the surface without any curvature. So why is all the the calculations based on flat surface? A method of computation is applied to the refraction in the case of a plane surface, and in this case of the Earth's surface, the method of successive approximation for each zenith distance. And when you start to go in the document, of course, you're going to have the situation based on a sphere, but a few times in the document, you're going to see all the time talking about flat Earth. And all the time. In fact, I think it's here said is coming from these calculations, and they say this. They say, okay, now we're going to address a case for the ideal surface, flat surface of the Earth, and all the time they trying to put like if we're gonna do something on the flat surface, that is unreal. It's not true, but we need to make it.
But we need to put it there anyway. And that's exactly the problem, Ira. That's what I was saying earlier. When you look at how the standard refraction is derived, it's all derived based on a flat surface. And why do they do that? Because that is precisely what we observe. So they do all their calculations, everything based on a flat surface because it's what we observe. And then they tell us that this is how it applies on a ball, which is ridiculous.
That's right. In fact, when you see all these documents, and any guy out there who is an astronomer or amateur astronomer, he knows that the best observation is from the 20 degrees up in the horizon. And that is because I took one of the page of the document by NASA, which is talking about the flat Earth. Here said the refraction is a plane parallel slab. The observer is at zero on the surface of the flat Earth. Refraction occurs at the top of the slab of the atmosphere. And this is from 0 to 25 degrees above the horizon. And when you see all the situation based on refraction, it's happened at that gradient. That is why if you see some objects like mountains or like city above the 25 degrees, is perfectly the image itself. It's not distorted, it's not illusion, it's not a mirage. It's the image, maybe is amplified because the atmosphere have that property. You also have the zoom of the camera, which compress the image. But all in any situation of atmospheric refraction, you're gonna see at that particular gradient. Above that, supposedly we have not, I don't say the 100% real image, but we don't need to lead with this standard atmospheric refraction. And in any example of the real life, you're gonna see object lift up at the horizon level.
Yes.
So when you see, let me just show something very quickly based on the I'm looking in the other monitor. Let me just
Okay.
here. I have here. For example, here you can see the typical sea or ocean situation compared with the, a guy ride his bike on the street, and all the time is at that particular gradient. There is, in fact, when you see from start, and this is take from the discussion thread of the Metabunk, you can clearly see when happened that big distortion at that area. And now we are like 2,000 meters above the sea level. But it's like a personal view. Anytime you point to the horizon is when the lines converge, is when they produce that effect.
Yep.
It's not
Exactly.
only based, what? Sorry?
I said exactly. Yes, that's correct.
That is why all the time happen there. It doesn't matter what is the altitude. You can go lower to the street, you can be lower at the beach level, and you can rise up 2,000 meters, and you're gonna have the same situation with the buildings, mountains, sun, moon, whatever. It's all the time is gonna happen there. In fact, something that for me, when you see this kind of pictures, for example, this is the Canigou seen from 270 kilometers at the altitude of 343 meters. There is a few more meters of the mountain that you never need, you don't see in the GLOBEBUSTER model. Of course, when you enter to softwares like the panorama generator or things like that, they assume that they have the 0.16 coefficient of standard refraction. So in their calculation, based on computer and software, you're gonna see a really good image like this. But where is the example where you can lift up an object 400 meters and see perfectly like this?
Yeah, there aren't any.
There aren't any.
So
Yeah.
that's why they say what you see here is a mirage.
It's a mirage. In fact, when you go for example, to total stations for make measurements, they say we assume index of refraction, the coefficient, from 0.14 to 0.2, which is too much. There is no any case that in real life supposedly you're gonna find more than 0.21, 0.23. That is why this kind of I'm sorry because it's in Spanish, but that is why you can you're never going to find situations in real life based on 0.3, for example, and some of our observations require that kind of coefficient. But for finish the presentation, the thing is they took for me, this is my opinion, but they simply know that the atmospheric refraction are standard in the way that all the time happen and distort the image in the in a gradient. So it's like they map that distortion and apply this coefficient situation to get big the Earth. So it's like okay, when we see objects that are impossible in the globe based on the 6,300 kilometers of the radio, well, we get bigger the Earth based on this little tiny coefficient to match the observation.
Yep.
So it's like the Einstein quote,
Yep, exactly. That and thus the 7/6 times the radius. So very good.
Yeah.
Okay.
And the last thing, just for finish, even when I found this little video from the university, and this is in the way that okay, the light is behave like, well, you can see the gradient of temperature where the inversion are produced and things like that. But any inversion is always on top of the 20 degrees above the horizon.
Yep.
You're never going to have the image inverted at the horizon level, and you're going to see the image inverted touching the horizon level. But this is what I want to show for finish the presentation. It's because all the time is this debate about, okay, it's a wave or it's a particle, the light, because that changed a few things. And for example, I all the time, you know, I come across with different opinion. And for example, this guy talking about optics, when they talking about optics, the light is a wave.
So the theory for a perfect lens actually originated in about the 1960s. A guy called Victor Veselago, he said that you could get something called a negative refractive index, which essentially means that when you look at a prism or something like that, light tends to bend a certain way. And he proposed that you could get light to bend the other way if you so wanted. And this is the basis behind a perfect lens. Current limitations with optical microscopy are mainly due to something called the diffraction limit, which was divided by a guy called Ernst Abbe in 1873. Now the problem with that is that light is a wave, and as a wave it diffracts in certain ways. And the diffraction limit means that you can only resolve down to a very small spot, but a fixed size of spot. So you can get to about 200 nanometers across, and that's about, well, we're talking millionths of a millimeter here. And you can't go any further than that due to the wave-like nature of light. So that's a big problem.
The refractive index of a material is how much light slows down when it travels through such a material. So the light is traveling from air and into water. And when it hits the surface, it reflects a little bit, but it also transmits, and it bends at an angle that's related to the difference in refractive index between the two materials. Now water and pretty much all materials in nature have what's called a positive refractive index. So what's happening here is the light is going from air into water, and you can see that the light is bending towards the normal when it enters the more dense material, which is the T. If this wasn't T, but a negative refractive index material, something different would happen. The light wouldn't be on the left-hand side of the normal, it would instead be on the right. So light would come in this way, but then bend back on the opposite side to the surface normal.
The actual idea for a perfect lens, for it to be used to image things, came up with a guy called Sir John Pendry in about late 1990s, and it was demonstrated in early 2000s. And this idea basically uses a metamaterial, so a material that's comprised of very small structures, much smaller than a wavelength of light. And by arranging those structures in certain ways, you can amplify light waves and get them to diffract the wrong way. And you can see images you wouldn't normally be able to see on a much smaller scale.
With nanotechnology, you're dealing with things that you can't see. So it's really important that you have these tools that allow you to see a nanoparticle inside a cell that's really complex. So if you're doing bulk measurements, just on a lab bench, it's difficult to interpret the results, and that's where microscopy and good optical or high-resolution optical microscopy and electron microscopy are so important, and more so now that we're dealing more with nanotechnology.
So we look at the interface between nanotechnology and immune cells using nanomaterials to try and control the responses where the body decides, the immune system decides whether it's going to attack an infection or a cancer or whether it's not going to. And the reason that's a nanotechnology or a nanoscale problem is because what these high-resolution microscopies are beginning to reveal is that there are a lot of exceedingly small structures, so down to the level of tens of nanometers or less. And these structures are critical to the way cells talk to each other. So when your immune system decides whether it's going to attack something, there are spatial structures at that size which are helping to mediate that decision. So the combination of, so the ability to image those is vital to understanding that, and it's also vital to understanding how to control that process if you want to for therapeutic reasons.
In our group, we're interested in looking at the interaction between a cell and nanoparticles. And you can't currently see that in the conventional optical microscope. But if you could watch where an individual nanoparticle is interacting with the cell, what compartments it's going into, what effect it has on the cell structure. That would be really interesting to do in a live cell.
And cells, when they're alive, they're generally quite transparent and colourless. So you'll have to stain them if you want to see them, and that is actually obviously influencing the cell itself. And you don't want to do that because then it starts messing with the processes.
Not only are the imaging techniques coming online, but also nanotechnology techniques that enable us to build structures on the same size as these vital structures mean that we can interact directly with these little features. We can control their size, help try to control their size, or to pull them around, or to position them. And so these two technologies coming in parallel should really show some exciting results.
Perfect lensing principles have actually been demonstrated already on things like up to maybe 20, 30 nanometers, which is already a good, something like 10 times below the diffraction limit. So we've shown that it works. It's just going to take a bit more time and maybe a little bit of someone's clever idea to make it actually a reality.
Here, this guy is talking about one of the most important physicists studying optics, which is Ernest Ave. I believe that is why we call aberration when the chromatic aberration happened. And he says, okay, Ernest Ave in 1873, he discovered that the light is a wave. Here is the word wave in Spanish. So they trying to use metamaterials to find the non-distortion lens, the ultimate, lens of the of the universe, to have no kind of distortion. So when they trying to make that, they treat the light as a wave, of course, not as particles. And I finish with this. I find this experiment based on the Michelson-Morley experiment, but this time the guy at the end of the laser, let me just go to the end of the experiment. When they show the image projected by the interferometer, they just simply take this dry hair and apply heat to that wave of light. And what happened is bent down.
Interesting.
So, exactly, because all the time we live with these temperature situations, and I just pointed out, because in the you can see how now the project light is down than was before, and the situation is when we see on the sunset, we are leading with infrared light, and infrared light it makes lower the light. Ultraviolet make quickly. So right. That is why all the mirage, all the superior mirage are always in the morning or in the daylight. Some rare case you're gonna find on the sunset times. So when we see objects like the skyline of Chicago or the Canigou are all in the situation of the sunsets. So you are leading with infrared, and infrared slow down the speed of light. So that is why I believe that they're never going to find a real example that the objects are lifting up in the control environment like we see all the time in the opposite way.
I totally agree with you. I'll close this part of the discussion out by saying that, I can already see this objection coming. Especially when you were talking about temperature gradients, the ballers are going to respond with, well, Bob, the thing that you didn't mention is that as you are climbing higher and higher and higher where that laser beam is, the temperature is getting cooler and cooler and cooler, which of course will lower the density altitude. And to that I say, you're absolutely correct. However, now this is where we get to borrow a page from NASA's excuses, except in this case it actually applies. Much like NASA says, well, you don't have to worry about the ISS being in the thermosphere because the molecular density of the air up there is so minuscule that it really doesn't make any difference and you don't have to worry about any heat convection, right? Well, sort of the same thing here. I mean, granted, we're not talking about the super high distances, but I will say that as you go higher and higher, obviously because of the fact that the air density is becoming lower and lower, the convection that would cause the overall density of the atmosphere to increase becomes more and more irrelevant, okay? So really what matters is the actual density figures that you can look up. But you can look these up anywhere. As you get up to, 6,000, 7,000 feet, it changes dramatically. And, I can tell you there's quite a dramatic change just between Colorado and any place on sea level. So just because I know that is going to be coming, I just wanted to address that.
Yeah, but all the time when you see object, okay, if you have like a cold temperature, you can have this bend upwards the light, but the object is all the time at the view. It just bend up or bend down, but the object is all the time at your, at your side.
Yeah. Oh, I agree.
If the object is not, the situation here is send us a real example of the object occluded and in different altitude rising up in this standard refraction situation.